Let's say that HA represents a generic weak acid and B represents a generic weak base. If our weak acid donates a proton to our weak base, that would form A- and Hb+. To identify conjugate acid-base pairs, remember there's only one proton or one H+ difference between an acid and its conjugate base. So when HA donates its proton and turns into A-, A- must be the conjugate base to HA. So there's one H+ difference between HA and A-. They are a conjugate acid-base pair. When B accepts a proton, it turns into Hb+. Therefore, Hb+ must be the conjugate acid to B. Since there's one H+ difference between B and Hb+, they are a conjugate acid-base pair. Let's look at the situation where the equilibrium constant for this reaction is greater than 1. If K is greater than 1, that means at equilibrium there are more products than reactants. Therefore, the equilibrium favors the formation of the products. For acid-base reactions, the equilibrium always favors the side with the weaker acid and the weaker base. Therefore, since the equilibrium favors the products, the weaker acid and the weaker base are on the product side, and the stronger acid and the stronger base are on the reactant side. So when comparing our two acids, HA and Hb+, HA is the stronger acid of the two. And when comparing our two bases, B and A-, B is the stronger base of the two. When the equilibrium constant is less than 1, that means at equilibrium there are more reactants than there are products. Therefore, this time the equilibrium favors the formation of the reactants. And the equilibrium always favors the side with the weaker acid and the weaker base. Since the equilibrium favors the reactants, the weaker acid and the weaker base are on the reactant side, and the stronger acid and the stronger base are on the product side. So comparing our two acids, HA and Hb+, this time Hb+ is the stronger acid of the two. And for our bases, B and A-, this time A- is the stronger base of the two. Let's look at an example of a weak acid-weak base reaction. The hydrogen sulfate anion will react with the carbonate anion to form the sulfate anion and the hydrogen carbonate anion. Looking at the reaction, the hydrogen sulfate anion is donating its proton, so that must be the acid, and the carbonate anion is accepting a proton, so that must be the base. After the hydrogen sulfate anion donates its proton, it turns into the sulfate anion, SO4 2-. Therefore, the sulfate anion must be the conjugate base to HSO4-. So one conjugate acid-base pair is HSO4- and SO4 2-. And when the carbonate anion accepts a proton, it turns into the hydrogen carbonate anion. Therefore, the hydrogen carbonate anion must be the conjugate acid to the carbonate anion. So our other conjugate acid-base pair consists of the carbonate anion and the hydrogen carbonate anion. The equilibrium constant for this reaction at 25 degrees Celsius is greater than 1. Therefore, the equilibrium favors the formation of the products. And because the equilibrium favors the formation of the weaker acid and the weaker base, we know that the weaker acid and the weaker base must be on the product side, and the stronger acid and the stronger base are on the reactant side. Therefore, the hydrogen sulfate anion is a stronger acid than the hydrogen carbonate anion, and the carbonate anion is a stronger base than the sulfate anion. Let's look at another example of a weak acid-weak base reaction. In this case, hydrofluoric acid reacts with ammonia to form the ammonium ion NH4+ and the fluoride anion F-. Because hydrofluoric acid donates a proton, it's an acid, and because ammonia accepts a proton, ammonia functions as a base. And when HF donates a proton, it turns into F-, the fluoride anion. Therefore, the fluoride anion is the conjugate base to HF. And when ammonia accepts a proton, it turns into NH4+, the ammonium ion. Therefore, the ammonium ion is the conjugate acid to NH3. Let's say that we mix equal moles of our weak acid HF with our weak base NH3, and our goal is to figure out if the resulting solution is acidic, basic, or neutral. First, we need to determine if the reactants or products are favored at equilibrium. And to help us determine that, here we have the Ka and Kb values for our acids and bases. So here's the Ka value for hydrofluoric acid at 25 degrees Celsius. So all these are at 25 degrees Celsius. Here's the Kb value for ammonia, the Ka value for the ammonium ion, and the Kb value for the fluoride anion. So looking at our two acids, that was hydrofluoric acid and the ammonium cation, the Ka for hydrofluoric acid is a higher value than the Ka for the ammonium cation. Therefore, hydrofluoric acid is the stronger of the two, the stronger acid of the two. And for the two bases, we have ammonia and we also have the fluoride anion. Looking at the Kb values, for ammonia, the Kb value is higher than the Kb value for the fluoride anion. Therefore, ammonia is the stronger base of the two. So we have the stronger acid and the stronger base on the reactant side, and the weaker acid and the weaker base on the product side. We know the equilibrium favors the side with the weaker acid and the weaker base. Therefore, the equilibrium favors the formation of the products. So we could go ahead and write the equilibrium constant for this reaction is greater than 1. And at equilibrium, we're going to have more of our products than we do of our reactants. So to determine if the solution is acidic, basic, or neutral, we have to think about the ammonium cation and the fluoride anion in aqueous solution. Since the Ka value for the ammonium cation is greater than the Kb value for the fluoride anion, the ammonium cation is better at producing hydronium ions in aqueous solution than the fluoride anion is at producing hydroxide anions in aqueous solution. So the concentration of hydronium ions will be greater than the concentration of hydroxide anions, and therefore the resulting solution will be acidic.